Okay, today we're going to look at a partial differential equation. This is part one. We'll be doing the heat equation. If these are popular, I'll do some more. But today we'll be discussing the heat equation as a partial differential equation. We will not be discussing any physics, so we're going to be doing pure math. So I'm just going to pretend like you're a mathematician. You don't know any physics. Why this equation is what it is, because we don't have time to discuss that. So if you were a mathematician and a teacher handed you this partial differential equation, what would be the first thing you would do? Just to make it a little bit more compact, we might rewrite it like this. So these are second partial derivative of u with respect to x, and here's u x means the second partial derivative of with respect to x of u, and here's the partial derivative of u with respect to t, and we write that as u sub t. So it's just a little bit nicer, more compact, less work to write all that out. Otherwise, the k squared stayed there. So the teacher gives me this, I simplify to this. In this lecture, we will be using something called the method of separation of variables, and our first step is to assume that u is a function of x times a function of a different function of t, not necessarily the same function. So we assume u equals f times f of x times g of t. Okay. And the first thing we'll do is we'll take two partial derivatives of this with respect to x, and two partial derivatives with x. The g of t will just be constant, so that nothing will happen to g, but there'll be two derivatives of x, the x function right here. So uxx equals f double prime times g. We'll take the partial derivative with respect to t of this function, and so f will be just hanging out, and we'll have g prime because g is a function of t, and we're taking the partial derivative with respect to t. So we'll have these two things. Why did we figure those two out? Well, because they're inside our equation right here. So here's our equation again. I wrote it again for just to make it convenient. So do you know who uxx is? Yeah, uxx is f double prime g. Why don't you take that and plug it into here and get this? That's nice. Do you know who k squared is? No, but I'll leave that alone. So I'll leave that alone. Do you know who partial u with respect to t is? Yeah, he's f g prime. There's f g prime. So for this, I'll plug that right into here and get this right there. That's what we'll do. Okay, can you do a little bit of algebra with this? Why don't you take all the f people and put them solve for f people and put all the g people. So I think algebraically this becomes this equation right here. And we're going to do something interesting. We're going to set these two equal to a constant, negative lambda. It's just more convenient to do the negative later on. You could have done a positive. It's just more convenient to do a negative there. So either one would be fine. Then what we'll do is we'll take these people right here and say, hey, they equal negative lambda. Here, those people equal negative lambda. And we're going to solve this differential equation. And this differential equation, if you look at I have a lecture on regular differential equations, not partial. We learned how to solve these. We can algebraically change it over to this, and this is a second order differential equation right here. And we can solve that if we assume lambda is positive, so that we don't get so we get the non-trivial solution. The solution to this is this right here. If you review your differential equations, or I have a lecture on differential equations where we solved one of these problems. Okay. That's because the roots of this will be imaginary, of course, if lambda is positive. Okay, so this is our solution for the f function. Let's take a look at the other equation. Remember this equation, we did this equation equals negative lambda. Now we're going to do this equation equals negative lambda. There it is, right there. You see that? So this equation equals negative lambda is right there. And we're going to solve that equation. And if we solve this equation, we do a little bit of algebra, we'll get this. And this is a this is a first order linear differential equation, which I also discussed in my differential equations video, if you want to go look that up or look up somebody else's. And the solution to this is this right here. We learned that in one of our videos. So we know F and we know G. If we know F and we know G and there's no derivatives in F and G, then we have we know who Mr. U is. Remember, we said U equals F times G. So U equals F. Here's F over here times Mr. G right here. Now, I crossed out the D right here. The reason why is because if I multiply the D times A, I'll just get a constant. And the D times B, I'll get a different constant, maybe. Not necessarily the same constant. So we don't need the D here. So we threw away the D here. This will give us a little bit more compact form. I'm going to rewrite this on the next page. So let's take a look at the next page. So this is our U function. It's F, function of X, times function of the function of G right here. G times the F function. There's our U function. All right. Okay, so here I've rewritten it without the D right here. Nice and clean. It's all nice and clean. We're going to look at something called boundary conditions. I'm going to take this a little bit further. You might say, hey, Vince, you told me in our differential equations video, if I have no derivatives, I'm done. Well, we're going to take it partial differential equations are a little bit different than regular differential equations. So we're going to take this a little bit further. We're going to talk about boundary conditions. We'll assume that, again, you're being a pure mathematician. U of 0t equals 0. So that means that x equals 0. So if we go up here, we say, hey, do you know who U is? And we say, yeah, U equals 0. So we'll plug a 0 in for that. Do you know who T is? Yeah, T is T, so we'll leave him alone. I just wrote this as garbage. There's a bunch of people up there. It's not going to matter. Do you know who X is? Yeah, X is 0. So plug a 0 in there. Cosine of 0, of course, is 1. And do you know who X is? Yeah, he's 0. Sine of 0 is equal to 0. So when you plug this boundary condition into this solution, you get this equation. And this equation, of course, will tell you that since this cannot be 0, A has to be equal to 0. So we get A equals 0, and that's going to simplify our equation here. That A needs to be 0. So all this whole island will go away, and sure enough, I've written the new solution without this island right here. So this is our new simplified solution according to this boundary condition. If this boundary condition changes, then this will change also, of course. This is not a generic solution. This is a more generic solution for the heat equation. This is a specific one to this particular problem, although most of the heat equations do have this boundary condition, but not all. The next thing we're going to talk about another boundary condition, and that is that we'll make U of P U of PT equal to 0 also, and this time X will equal P. So we'll go up to this equation, and we'll say, hey, do you know who U is? And yeah, U equals 0, so we'll put a 0. Do you know who T is? Yeah, T is just T, so we'll leave that alone. It's a bunch of garbage. By the way, I know you guys are going, why don't you tell me who lambda is or K squared is? Right now, they don't matter, so we'll just leave them alone. It's lambda and K squared. That's what I mean by all of this garbage. I didn't want to rewrite it. It's all of this stuff. All of that stuff is this garbage. It's unnecessary, so I didn't want to write it. Do you know who Mr. B is? No, I don't know who Mr. B is. Do you know who Mr. X is? Yeah, Mr. X is P. And lambda, we'll just leave him alone. I don't know who he is. So when you don't know somebody, you just leave him alone. Well, e to the something can't be 0, mathematically, as you well know. And also b can't be 0, because if b is 0, we just get u equals 0 as the solution to our problem, and that's not going to be very productive. So it's going to have to be the sine of p square root of lambda has to equal 0. Well, the sine has to eat what to make it 0? Well, if the sine eats pi, it becomes 0. 2 pi becomes 0, 3 pi becomes 0. So if the sine, if inside the stomach of the sine, you have 1, 2, 3, or n pi, any n pi, like 75 pi, yep, sine of 75 pi equals 0. So if this inside equals n pi, if p square root of lambda equals n pi, then this equation will be true. If p square root of lambda equals 3 pi over 2, then no, this won't be true. So we're forcing this sine function, finding out what argument this is, to force this sine function to be equal to 0. And the only thing this argument can be is equal to n pi, not n pi over 2 or n pi over 7 or 3n pi over 15. It cannot be any of those things. It has to be an integer times pi. And what we're going to do is solve for lambda here. So if you do a little bit of algebra and solve for lambda, you get this. Why did we do all that? Well, because remember, we made up Mr. Lambda. So we're not allowed to put that in a solution. But the teacher gave me Mr. P. The teacher gives me this initial condition. We did make up n, but n is forced. It has to be that way. So now we can replace the lambda that we just created inside the solution right here. So let's take our solution, and wherever there's lambda, see the lambda there and the lambda there, we're going to plug this into here, and we're going to plug this into there, because that's lambda, and that's lambda, and that's lambda. So let's see what our new solution looks like. And here we go. Notice the lambda is gone here, and the n squared, pi squared, p squared is right there. There it is right there. And if you, by the way, lambda equals this, the square root of lambda equals n pi over p. So right here, where we had a square root of lambda, remember that square root of lambda right there? We won't put this, of course, so we have to put this inside the square root. I did the work for you. So the square root of lambda is equal to n pi over p. So right here, we put n pi over p, this guy right here. Okay. So we put lambda into here and got this. We put square root of lambda into here and got this. So this is our new solution. We like it much better because it doesn't have that made-up lambda guy that we just created out of thin air. Okay. Well, the first thing we notice about this is that this solution does have an n in it. And if it has an n in it, an index like that, the b doesn't necessarily there's many different solutions, an infinite number of solutions here. So one solution for u is make n 1 and 1. Another solution is 2 and 2. 3 and 3 put in for n. So there's millions and millions of solutions to u. But the coefficient b doesn't have to be the same. You're forcing it to be the same if you don't index it with an n. So that means that when it's 1 and 1, n is 1 and 1, then maybe b is 14. But when n is 2 and 2, maybe b is negative 75. So we have to index b, so we're changing b from one constant to an infinite number of constants, so that each of the solutions, 1 and 1 or 2 and 2, has a possible different coefficient. Okay. So, by the way, and that's nice that we have this, but the better way to write this solution with the principle of superposition is that the solution to our heat equation is that all of these solutions added up, the sum of all these infinite solutions is actually the most generic solution to the equation, and we're going to sum this, of course, with a summation. And we'll start with n equals 1, because we can't start with n equals 0, otherwise we'll have 0, and that'll be a little bit silly. So we'll start with n equals 1 is the first possibility for n, and we'll go to infinity, the sum from 1 to infinity of this all these solutions. So this is an infinite series of the solution. We will stop here, even though we have not found out who the b sub n is. That would be our next step. I'm going to stop here because to find b sub n, we have to use a Fourier series, and that's a huge lecture on its own, and I don't want to, this is already at 16, 17 minutes, and I wanted to keep it a little bit short. So we will use Fourier series to solve for all b sub n's for a specific initial temperature function. And we'll do that in another lecture. I hope you enjoyed this. I looked forward to any comments at the bottom, and thank you for watching. Goodbye.